Hi everyone, welcome back to my channel. This is the second video in computer graphics. So in this video, we are discussing about 2D pipeline, 3D pipeline, RGB color model, and CMY color modeling. So first is 2D pipeline. The mapping of two-dimensional world coordinates scene description to device coordinate is called two-dimensional viewing transformation. Sometimes this transformation is simply referred to as the window to viewport transformation or the window transformation. But in general, viewing involves more than just the transformation from clipping window coordinates to viewport coordinates. In analogy with three-dimensional viewing, we can describe the steps for two-dimensional viewing as indicated in the diagram. So you can see in the diagram how the steps are shown. Once a world coordinate scene has been constructed, we could set up a separate two-dimensional viewing coordinate reference frame for specifying the clipping window. But the clipping window is often just defined in world coordinates, so the viewing coordinates for the two-dimensional application are same as the world coordinates. So to take the viewing process independent of the requirements of any output device, graphics systems convert object description to normalized coordinates and apply the clipping routines. Some systems use normalized coordinates in the range from 0 to 1 and others use normalized range from -1 to 1. Depending upon the graphics library in use, the viewport is defined either in a normalized coordinate or in screen coordinates after the normalization process. At the final step of viewing transformation, the contents of the viewport are transferred to the position with the display window. Clipping is usually performed in normalized coordinates. So this allows us to reduce computation by first concatenating the various transformation matrices. Clipping procedures are of fundamental importance in computer graphics, so they are used not only in viewing transformation but also in window manager systems, in painting and drawing packages to erase picture sections, and in many other applications. So now let us see the 3D pipeline. So clipping windows, viewports, and display windows are usually specified as rectangles with their edges parallel to coordinate axis. So in three-dimensional viewing, however, the clipping window is positioned on a selected view plane and scenes are clipped against an enclosing volume of space which is defined by a set of clipping planes. A viewing position, view plane, clipping window, and clipping planes are all specified within the viewing coordinate reference frame. So you can see in the diagram, this diagram shows the general processing steps for creating and transforming a three-dimensional scene to device coordinates. Once scene has been modeled, the world coordinates a viewing coordinate system. The viewing coordinate system defines the viewing parameters, including the position and the orientation of the projection plane, which we can think of as the camera film plane. A two-dimensional clipping window corresponding to a selected camera lens is defined on the projection plane and a three-dimensional clipping region is established. This clipping region is called the view volume and its shape and size depends on the dimension of the clipping window. The type of projection we chose and selected limiting positions along the viewing direction. Projection operations are performed to convert the viewing coordinate description of the scene to coordinate position on the projection plane. Objects are mapped to normalized coordinates and all parts of scene outside the view volume are clipped off. The clipping operations can be applied after all device independent coordinate transformations are completed. So in this way, the coordinate transformation can be concatenated for maximum efficiency. So now let us see the RGB color model. According to the tristimulus theory of vision, our eyes perceive color through the simulation of three visual pigments in the cones of the retina. One of the pigments is most sensitive to light with a wavelength of about 360 nanometer, that is red. Another, it is peak sensitivity at about 530 nanometer, that is green. And the third pigment is most respectively to light with a wavelength of about 450 nanometer, that is blue. By comparing intensities in a light source, we perceive the color of the light. This theory of vision is basis for displaying color output on a video monitor using the three primaries red, green, and blue, which is referred to as the RGB color model. We can represent this model using the light unit cube defined on RGB axis. As shown in the diagram, the origin represents black and the diagonally opposite vertex with coordinates 1, 1, 1 is white. Vertices of the cube on the axis represent the color primary, and the remaining vertices are the complementary color points for each primary colors. So these are the complementary color points. Cyan, magenta, and yellow are the complementary colors. So this is RGB color model. So now let us see the CMY color model. A video monitor displays color patterns by combining light that is emitted from the screen phosphorus, which is an additive process. However, hard copy devices such as printers and plotters produce a color picture by coating a paper with color pigments. We see the color patterns on the paper by reflected light, which is a subtractive process. So a subtractive color model. So CMY color model is also called as subtractive color model. It can be formed with the three primary colors, cyan, magenta, and yellow. So as we have noted, cyan can be described as a combination of green and blue. So it is a combination of green and blue is cyan, and therefore when white light is reflected from cyan color ink, the reflected light contains only the green and blue components, and the red component is absorbed or subtracted by the ink. Similarly, magenta ink subtracts the green component from incident light, and yellow subtracts the blue component. A unit cube representation for the CMY model is illustrated in the figure. So in the CMY model, the spatial position 111 represents black because all components of incident light are subtracted. The origin represents white light, equal amounts of which these primary colors produce shades of gray along the main diagonal of cube. A combination of cyan and magenta ink produces blue light because the red and green components of incident light are absorbed. Similarly, combination of cyan and yellow ink produces green light, and combination of magenta and yellow ink yields red light. So this is all about the CMY model. So you can compare the RGB and CMY model in this figure, how it looks. So this is how it looks. This is how it is different. Thank you.